The purpose of this lab was to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We can predict the motion using fundamental principles such as the energy principle and Newton's second law, in combination with other equations, such as Hooke's law. The video of Dr. Greco dropping the mass was imported into Tracker to be further analyzed. An XY plane was added with the origin on the top of the spring falling in the negative Y direction. A calibration stick was added as the length of the spring to provide a frame of reference, with length 0.7 meters. As the spring oscillates, the center of mass was recorded and the data was saved in a CSV file to be iterated through later. With the experimental oscillation, and they were then compared. Within the Python code, several principles were used to calculate the ideal model. The initial conditions were first changed, including the ball's mass, which is 0.402 kilograms, and the initial position of the ball before Dr. Greco releases it, which is negative 0.11, negative 0.642, and 0. Stiffness constant K was then solved for using the equation T equals 2 pi times the square root of m divided by K. One period of oscillation calculated in the tracker video was found to be 1.52 seconds, and when the mass of 0.402 is plugged into the equation, K is found to be 6.87. From here, the known forces interacting with the mass are the Earth and the spring. With this knowledge, the force of the spring is set equal to the force of the Earth. Hooke's law is applied here as Ks is set equal to mg, solving for LO in the equation. LO is found to be 0.127 meters. The system energies are then solved for using the equations Ke equals 0.5 mv squared, Ug equals mgy, and Us equals 0.5 ks squared, with E equaling Ke plus Ug plus Us, and E is the total energy of the system. Calculated using the spring force, including the spring force using Hooke's law and the force of gravity. The net force is found by adding both of them. The initial energies are found as well. Then, using Newton's second law, the ball's new velocity and then the corresponding position could be calculated. So the final velocity equals the initial velocity plus F net divided by m times delta t, and then the position is calculated by the final position equals the initial position plus the ball's velocity times delta t. The constantly changing energies are calculated for the ideal model as well, subtracting the initial from the final to obtain the change in energies, shown here. The virtual model of the ideal mass and the experimental mass show the experimental mass, the red ball, following the blue ball, the ideal mass. This difference is most likely due to human error, like not placing the center of masses precisely in the tracker video. The ideal model also doesn't take into account the drag force. The graphs showing the difference in positions also note this. The first what does it mean question asks if the energy principle is satisfied. So the graphs of the energy show the change in kinetic energy oscillating at the same magnitude of the change in potential energy of the spring, but in the positive direction, while the potential energy oscillates in the negative direction initially. The total energy line, the yellow line, is 0, and this means that energy is conserved, meaning that no energy left or entered the system. This means that the Earth's energy was included in the system's energies. Therefore, we know the energy principle is satisfied, since it states that the change in total energy equals the change in kinetic energy plus the change in potential energy of the spring plus the change in potential energy of the Earth, which should equal 0. Since all three change in energies add up to 0, the principle was satisfied. For the second what does it mean question, it asks to find the two separate estimates of oscillation periods. And the first oscillation period for the X data was estimated to be 1.52 seconds, and the oscillation period for the Y data was estimated to be 1.33 seconds. This is because there are two different formulas to calculate the oscillation period for the X data versus the oscillation period for the Y data. The X data equation is T equals 2 pi times the square root of m divided by k, versus for the y position, it is t equals 2 pi times the square root of L divided by g. Since two different equations are used, two different t values are found.